The topic of my report today is an ECG-based artificial intelligence model for assessment of sudden cardiac death risk. Here are the publication details, and this article was published in Nature Communication on February 27, 2024. First one is objective of the research. Sudden cardiac death occurs when there are problems with the electrical activity within the heart and is a major global public health problem. Conventional ECG-based algorithm could contribute to SCD risk stratification, but demonstrate moderate predictive capabilities. So this study using deep learning models, which can use the entire digital signal and could potentially improve predictive power. Thus, they expect this deep learning model to enable regular monitoring of these individuals, potentially preventing sudden cardiac death in some cases. The dataset in this study used two geographically separate community-based prospective and ongoing studies of out-of-hospital SCDs in the general population. One is Oregon South for training, validation, and testing, and the other is Ventura Presto for external validation. The flowchart below shows the data collection method used in this study. Potential SCD cases in the community are identified in collaboration with regional EMS system. Trained physician researchers then confirm the likely cardiac etiology using all available medical record data from Oregon and California. This figure shows that ECGs with past rhythm, atrial fibrillation, or atrial flutter were excluded a priori from both internal and external cohorts to create a deep learning model applicable to ECGs in sinus rhythm. So we can see a total of 1,827 precardiac arrests 12-lead ECGs, from 1,796 SCD cases in internal cohort. As for external cohort, external validation was performed in 714 ECGs from 714 SCD cases from Ventura. Given that coronary artery disease, which is CAD, is the most common underlying substrate of SCD, they recruited control subjects from the Portland, Oregon metro area to represent individuals at intermediate risk of SCD, with a large proportion having CAD. The figure shows two separate control group samples were obtained from 1,342 ECGs taken from 1,325 individuals, of which at least 50% have established coronary arterial disease. Next is the model architecture. In this research, they utilized PreOpNet, designed to analyze 12-lead ECG waveform data. The deep learning model employed convolutional layers following initial atrial layers, organized in an inverted residual structure. This model features input and output bottleneck layers with an intermediate expansion layer. To integrate the information across the 12-lead ECGs, the number of input channels progressively increased within each set of expansion layer, which were preceded by bottleneck layers. This approach has several advantages, including limiting the number of layers to less than 1/10 the size of previous architectures, thereby minimizing model complexity and optimizing runtime, resulting in a lightweight architecture while still maximizing performance. On the right table shows the performance and computational complexity of deep learning models, and the PreOpNet architecture is less than a fifth of the size of previous models and efficient enough to be run on a standard computer. In the results section, the Deep learning model achieved an AURC of 0.889 on the internal testing dataset and 0.82 on the external validation dataset for detecting NCD cases from controls. Additionally, they compared the deep learning model's performance to a previous developed and validated 6-variable ECG electrical risk score. The table shows that the conventional ECG electric risk score achieved an AURC of 0.712 on the internal testing dataset and 0.743 on the external validation dataset for detecting SCDs from controls. Below is the figure illustrating the AURC curves for identifying SCD cases in both the internal and external cohorts. Furthermore, to evaluate the predictive power of DL-ECG index beyond conventional clinical SCD risk factors, they perform logistic regression analysis, including clinical variables with and without DL-ECG analyzed output value, which is DL-ECG, in the internal and external dataset. As the slide shows, in the internal test dataset, adding a DL-ECG index to clinical variables improved the discriminative value for SCD from an AURC of 0.78 to 0.919. Similar results were obtained in the external test set, where the addition of the DL-ECG index to clinical variables improved the discriminative value for SCD from an AURC of 0.06 to 0.899. This figure shows the utility of the deep learning ECG index beyond clinical risk predictors. It illustrates the AURC curves for identifying sudden cardiac death cases in the internal and external cohorts using logistic regression models. In the discussion of the deep learning model for ECG analysis, the advantage including higher accuracy compared to traditional ECG risk score, the ability to use the entire digital signal without manual feature extraction, and fewer assumptions about data structure, leading to better evaluation of complex relationships. However, the disadvantage are the model's specific requirements for input data, vulnerability to system bias, and the current lack of interpretability of the mechanism behind the findings. To compare the architecture of models, I select a paper on mortality risk prediction for comparison. Both models use 12-lead ECGs as input data, although their objectives differ. One model is for mortality risk prediction, while the other is for SCD prediction. In the mortality risk prediction paper, the main components used are receiver and pooling modules and an attention module. In contrast, the SCD prediction paper primarily employs bottleneck and inverted receiver structures. This slide shows the model architecture used in the two respective papers that I mentioned previous. The left model is more complex, incorporating various modules such as receiver modules, SE modules, and attention modules, making it suitable for tasks requiring high precision and deep feature extraction. The right model, on the other hand, emphasizes efficiency, primarily using mobile bottleneck layers and pooling layers, making it ideal for resource-constrained applications like health monitoring on mobile devices. In terms of model performance, the model on the left achieved an AUC of 0.894 for ECG risk prediction, using a survival deep learning model, while the model on the right achieved an AURC of 0.889.